Sun. The Sun is a star at the center of the solar system. It has a diameter of about 1.4 million kilometers, 870,000 miles, making it roughly 109 times the diameter of Earth. The Sun is about 4.6 billion years old and is classified as a G-type main sequence star, meaning it generates energy through nuclear fusion of hydrogen into helium in its core. The Sun's surface, known as the photosphere, has a temperature of about 5,500 degrees Celsius (9,932 degrees Fahrenheit), while its core is estimated to have a temperature of around 15 million degrees Celsius (27 million degrees Fahrenheit). The Sun's energy output is so immense that it produces a wide range of radiation, including light, radio waves, and X-rays. The Sun is essential for life on Earth, providing energy for photosynthesis in plants and warmth for all living things. It also affects our climate and weather patterns. However, exposure to its radiation can be harmful and cause skin damage or even cancer. Scientists continue to study the Sun and its behavior to better understand its impact on our planet and the wider universe. Structure of Sun. The Sun is composed of several layers with varying characteristics, including temperature, pressure, and density. From the inside out, these layers are: core. The core is the central region of the Sun, where nuclear fusion reactions take place. It is the hottest and most dense region of the Sun, with temperatures reaching up to 15 million degrees Celsius (27 million degrees Fahrenheit). Radiative zone. Surrounding the core is the radiative zone, where energy produced in the core is transported outward by radiation. Convective zone. Above the radiative zone is the convective zone, where energy is transported outward by convection, or the movement of hot material. This region is characterized by large-scale motions and is responsible for the Sun's magnetic field. Photosphere. The photosphere is the visible surface of the Sun, where light is emitted. This region has a temperature of about 5,500 degrees Celsius (9,932 degrees Fahrenheit) and a density much lower than that of the previous layers. Chromosphere. Above the photosphere is the chromosphere, a thin layer of gas with a temperature ranging from 4,000 to 10,000 degrees Celsius (7,232 to 18,032 degrees Fahrenheit). This layer is visible during solar eclipses as a red ring around the Sun. Corona. The outermost layer of the Sun is the corona, which extends millions of kilometers into space. It has a temperature of over 1 million degrees Celsius (1.8 million degrees Fahrenheit) and is the source of the solar wind, a stream of charged particles that flows outward from the Sun into space. Overall, the Sun's structure is dynamic and constantly changing, as energy is generated and transported through its various layers. Sun's composition. The Sun is a massive, luminous ball of hot plasma, comprising almost 99.9% of the total mass in the solar system. It is composed primarily of hydrogen, about 73% of its mass, with helium making up about 25% of its mass. Other elements such as oxygen, carbon, neon, and iron make up the remaining 2% of its mass. The Sun has three main layers, which are the core, the radiative zone, and the convective zone. The core is the innermost layer, where the nuclear fusion reactions occur, converting hydrogen into helium and releasing a massive amount of energy in the process. The radiative zone is the middle layer, where the energy produced in the core is transported outward by the movement of photons. The convective zone is the outermost layer, where hot plasma rises and cooler plasma sinks, creating a circulating flow that transports energy to the surface. The Sun also has a complex magnetic field, with regions of intense magnetic activity known as sunspots. These magnetic fields can cause solar flares and coronal mass ejections, which can have a significant impact on the Earth's space environment and technology. Overall, the composition of the Sun is a fascinating subject that continues to be studied and researched by scientists around the world. Fusion Sun. The Sun's energy is produced through a process called nuclear fusion, which involves the combination of hydrogen atoms to form helium atoms. This process releases a tremendous amount of energy in the form of light and heat. In the Sun's core, temperatures and pressures are extremely high, allowing hydrogen nuclei, or protons, to overcome their natural repulsion and come close enough together to fuse into helium. This process is known as the proton-proton chain reaction, and it is the primary mechanism by which the Sun produces energy. The proton-proton chain reaction begins with the fusion of two protons, which produces a deuterium nucleus, or a heavy hydrogen nucleus, and a positron, which is a positively charged electron. The deuterium nucleus then fuses with another proton to form helium-3, which then combines with another helium-3 nucleus to form helium-4, the stable end product of the fusion process. In this process, two protons are converted into a helium-4 nucleus, releasing energy in the form of gamma rays. The energy produced by nuclear fusion in the Sun is what provides heat and light to the Earth, and it is also the source of the solar wind and other phenomena in our solar system. Scientists are studying fusion as a potential source of clean, sustainable energy for our planet, but so far, no practical fusion power plants have been developed. Radiative zone Sun. The radiative zone is a layer of the Sun that extends outward from the core to a distance of about 0.7 solar radii, or about 500,000 kilometers from the center of the Sun. It is a layer where energy produced by nuclear fusion in the core is transported outward by the movement of photons. In the radiative zone, the temperature is extremely high, around 7 million kelvins, and the density is also very high, around 20 times the density of gold. At these extreme conditions, the photons produced by nuclear fusion are quickly absorbed and re-emitted by the surrounding matter in a process called radiative transfer. This process takes millions of years to transport the energy from the core to the outer layers of the Sun. The radiative zone is also characterized by a slow and gradual increase in temperature as you move outward, with temperatures rising from about 2 million kelvins near the core to about 4 million kelvins near the boundary with the convective zone. This gradual increase in temperature is due to the transfer of heat through the radiative transfer process. Overall, the radiative zone is a crucial layer in the Sun's structure, as it is responsible for transporting the energy produced in the core to the outer layers of the Sun, where it is eventually radiated into space as heat and light. Atmosphere and Sun. The atmosphere is the layer of gases that surrounds the Earth and is held in place by gravity. It is composed of several different layers, each with its own unique properties and characteristics. The layer closest to the Earth's surface is called the troposphere, where we live and breathe, and it extends up to an altitude of about 10–15 kilometers. The Sun, on the other hand, is a star that is located at the center of our solar system. It is a massive ball of gas and plasma that emits light and heat through nuclear fusion reactions that occur in its core. The Sun's energy is essential for life on Earth, as it drives the Earth's climate and weather patterns, and provides the energy that fuels photosynthesis in plants. The interaction between the Sun and the Earth's atmosphere is complex and plays a critical role in shaping our planet's climate and weather. For example, the Sun's energy heats up the Earth's surface, which in turn causes the air to rise and creates areas of low and high pressure that drive wind and weather patterns. The atmosphere also protects us from harmful solar radiation, which can cause damage to living organisms and technological infrastructure if it reaches the Earth's surface. Sunlight and neutron. Sunlight and neutrinos are both products of the Sun, but they are fundamentally different phenomena. Sunlight, also known as solar radiation, is the electromagnetic radiation emitted by the Sun, which includes visible light, ultraviolet radiation, and infrared radiation. It is the primary source of energy that drives the Earth's climate and weather patterns, and is also essential for the process of photosynthesis in plants. Neutrinos, on the other hand, are subatomic particles that are created in the nuclear reactions that take place in the core of the Sun. They are electrically neutral, have a very small mass, and interact very weakly with matter, which makes them very difficult to detect. Neutrinos are constantly streaming through the Earth, and billions of them pass through our bodies every second without any noticeable effect. Despite their differences, both sunlight and neutrinos provide important insights into the workings of the Sun and the universe as a whole. For example, studying the properties of sunlight can help us better understand the Sun's energy output and its impact on Earth's climate, while detecting neutrinos can provide insights into the nuclear reactions that take place in the Sun's core and shed light on the nature of the universe's most fundamental particles. Magnetic activity. Sun. The Sun is a highly magnetic and active star, with its magnetic activity playing a crucial role in many important phenomena that occur on and around the Sun. Some of the key features of the Sun's magnetic activity include sunspots. These are dark regions on the Sun's surface that are caused by intense magnetic fields that inhibit the flow of heat from the Sun's interior. Sunspots are associated with solar flares and coronal mass ejection (CME), which can cause disturbances in Earth's magnetic field and affect our satellites and power grids. Solar flares. These are explosive bursts of energy that occur when the magnetic fields on the Sun's surface become highly twisted and tangled. Solar flares release large amounts of energy in the form of light, heat, and charged particles, and can cause radio blackouts and other disruptions to communications and navigation systems. Coronal mass ejection (CME). These are massive eruptions of plasma and magnetic fields from the Sun's corona outer atmosphere that can travel through space and interact with Earth's magnetic field. CME can cause geomagnetic storms, which can disrupt radio and GPS signals, damage satellites, and even cause power outages on Earth. Solar wind. This is a stream of charged particles, mostly protons and electrons, that flows continuously from the Sun's corona out into space. The solar wind is also influenced by the Sun's magnetic field and can cause geomagnetic storms when it interacts with Earth's magnetic field. Scientists study the Sun's magnetic activity using a variety of instruments and techniques, including telescopes that can observe the Sun in different wavelengths of light, spacecraft that can measure the solar wind and magnetic fields directly, and computer simulations that can model the complex behavior of the Sun's magnetic field. Understanding the Sun's magnetic activity is crucial for predicting space weather and its effects on Earth and our technological infrastructure. Sunspot. Sunspots are dark regions on the Sun's photosphere visible surface that are caused by intense magnetic activity. They appear as dark, cooler areas compared to the surrounding hotter regions of the photosphere. Sunspots are caused by magnetic fields that inhibit the flow of heat from the Sun's interior, which leads to a decrease in temperature in the affected regions. Sunspots can vary in size from small dots to large clusters that can be several times the size of Earth. They also vary in number over an 11-year cycle, with periods of high and low activity. During periods of high activity, sunspots are more common, and they can be visible to the naked eye. Sunspots are associated with other phenomena on the Sun, such as solar flares and coronal mass ejection (CME). When the magnetic fields in sunspots become highly twisted and tangled, they can release bursts of energy in the form of solar flares and CME, which can cause disturbances in Earth's magnetic field and affect our satellites and power grids. Scientists study sunspots using a variety of instruments and techniques, including telescopes that can observe the Sun in different wavelengths of light and spacecraft that can measure the Sun's magnetic fields and other properties directly. Understanding the behavior of sunspots and their associated phenomena is important for predicting space weather and its effects on Earth and our technological infrastructure. Solar activity. Sun. Solar activity refers to the various phenomena that occur on and around the Sun, which are driven by the Sun's magnetic fields and the flow of plasma ionized gas in the Sun's atmosphere. Some of the key features of solar activity include sunspots. These are dark regions on the Sun's surface that are caused by intense magnetic fields that inhibit the flow of heat from the Sun's interior. Sunspots are associated with solar flares and coronal mass ejection (CME), which can cause disturbances in Earth's magnetic field and affect our satellites and power grids. Solar flares. These are explosive bursts of energy that occur when the magnetic fields on the Sun's surface become highly twisted and tangled. Solar flares release large amounts of energy in the form of light, heat, and charged particles, and can cause radio blackouts and other disruptions to communications and navigation systems. Coronal mass ejection (CME). These are massive eruptions of plasma and magnetic fields from the Sun's corona outer atmosphere that can travel through space and interact with Earth's magnetic field. CME can cause geomagnetic storms, which can disrupt radio and GPS signals, damage satellites, and even cause power outages on Earth. Solar wind. This is a stream of charged particles, mostly protons and electrons, that flows continuously from the sun's corona out into space. The solar wind is also influenced by the sun's magnetic field and can cause geomagnetic storms when it interacts with Earth's magnetic field. The level of solar activity varies over an 11-year cycle, with periods of high and low activity. During periods of high activity, there are more sunspots, solar flares, and CME, and the solar wind is stronger. This can lead to increased space weather effects on Earth, such as auroras and geomagnetic storms. Scientists study solar activity using a variety of instruments and techniques, including telescopes that can observe the sun in different wavelengths of light, spacecraft that can measure the solar wind and magnetic fields directly, and computer simulations that can model the complex behavior of the sun's magnetic field. Understanding solar activity is crucial for predicting space weather and its effects on Earth and our technological infrastructure. Formation. Sun. The sun, like all stars, formed from a giant cloud of gas and dust known as a molecular cloud. These clouds contain hydrogen, helium, and small amounts of other elements such as carbon, oxygen, and nitrogen, which were produced by earlier generations of stars. The formation of the Sun began around 4.6 billion years ago, when a nearby supernova explosion triggered the collapse of a small part of the molecular cloud. The gravitational forces caused the cloud to contract and spin faster, forming a flattened disk of gas and dust around a central protostar, which eventually became the Sun. As the protostar continued to contract, its gravitational energy was converted into heat, causing the temperature in the core to increase. When the temperature reached about 10 million degrees Celsius, nuclear fusion reactions began to occur, and the Sun began to shine. Over time, the remaining gas and dust in the disk around the Sun gradually clumped together to form planets and other bodies in our solar system. The process of planet formation is still not completely understood, but it is thought to involve a combination of gravitational attraction, collisions, and other physical processes. Today, the Sun is a mature star that is about 4.6 billion years old and is in the middle of its main sequence phase, where it fuses hydrogen into helium in its core. It will continue to shine for several billion more years before eventually running out of fuel and evolving into a red giant star. To get more informational videos like this, please subscribe our channel, share and press the bell icon. Thanks for watching.